Okay, alright. Welcome to Lab 4, Physics 2211. The purpose of this lab is to examine a mass oscillating on a spring. We examine the motion of this system and create a computational model as well from the data gathered from the experiment. And then we also observe the changes of energy on this system. And results from this lab, as you can see from the bottom, is that the experimental computational models resulted in nearly identical movement of the system, the mass on the spring, and also the change in energy was zero throughout. Concepts used in this lab, we have the momentum principle, which is F net is equal to change in momentum or change in time. The energy principle, change in energy is equal to work done on the system plus heat transfers in the system. And for our lab today, we have three different energies that we account for: kinetic, change in gravitational potential, and spring potential. And the equation for them are given right here as well. And also two other relevant equations for this lab is the position update and the velocity update formulas right there. And here we have our tracker demonstration. I'm going to go ahead and play the video for you. You can see how I plotted out. And the system was the mass, spring, and earth, and surroundings is everything else. The initial conditions, the position we got from the tracker video, negative 0.114 for the x, negative 0.624 for the y, and 0 for z. Velocity was 0 throughout as it's starting from rest. The mass of the mass on the spring is 0.402 kilograms, and the spring stiffness is 6.83 newtons per meter. The relaxed length of the spring, or L naught, is 0.123 meters as well. And for our code, I've highlighted everything that I changed. We added the ball mass, the initial position and velocity, and then the delta t 1 over the frame rate times 20. We also added the gravitational constant, spring constant, and the L naught. And then we calculated the L vector, the length of the spring, the L hat vector, which is L over its magnitude, the L vector over its magnitude, and then S, which is the magnitude minus L naught. And also, I added the formulas for the energies in the system. Kinetic is 1/2 mv squared. Gravitational potential is mgh, or y. And spring potential is 1/2 ks squared, or k being the spring constant. And the total energy is all of them added up. And then in the calculation loop, we define the initial energies, find the force of gravity, which is negative mg in the y direction, the force of the spring, which is negative ks times the L hat vector, or the unit vector, and then the F net is the gravity and spring forces added together. We also have the velocity and position update formulas below, and then we update the spring to find the new L vector, and then in so doing find the new unit vector and the new S component. And then we also calculate the change in energy for each of the energies: kinetic, gravity, and spring, and the total. And we do that by calculating the energies again by using their respective formulas and then subtracting them from the initial that we did at the beginning of the calculation loop. And for our results, you can see on the left we have a change in energy versus time for the mass, and you can see the energy stayed constant throughout at a 0. And over on the right, you see two graphs, one for x at the top and one for y at the bottom. And they're very similar for both the experiment and computational, but they do differ slightly in the y graph, as you can tell. And this is due to some sources of error. Two possible sources of error that come to mind are during the tracker demonstration and calculating the energy principle. During the tracker demonstration, I was locating the center of mass manually, and this could have caused the data to deviate slightly. And the energy principle error is that we didn't account for any other forces like drag or any other energies that were acting on the mass or the system in total, and that could have caused it to differ. So for the what does it mean questions, the first question was the energy principle satisfied? I think it was. I say yes that it was, because there was no work acting on it and no heat exchange acting on the system. So delta E is equal to 0, as work and heat transfer are both 0. And for the second one, the estimating oscillation periods for the x position graph, when you take the average of the first 4 periods from the results that we did from our code, we get 1.66 seconds. And similarly for the y position graph, we get 1.52 seconds. And taking the difference, we get 0.14, and this could have caused the spring stiffness and the relaxed length of the spring to be different. As you can tell from their formulas, the spring stiffness uses the period and the relaxed length uses the spring stiffness. So changing one could have changed both, or changing the period could have changed both of those values. And that'll be all. Have a great day.